Hello, I'm John Shavacco, the co-chair of the NY-GEO 2023 conference and a board member of the New York Geothermal Energy Organization. I'd like to welcome you to this recording of a live presentation from the conference, a two-day event which was held in Albany, New York on April 26th and 27th of 2023. This year's educational sessions and keynotes represent the latest in ground source heat pump system design, product innovations, and installation practices, along with important policy, regulatory, financing, and incentive updates. This presentation is one of over 40 sessions from the two-day event, all of which were recorded and available at NY-GEO's website, www.ny-geo.org, along with session descriptions and a link to download the slides from each of the sessions presented. NY-GEO is proud to make this content available to our members and other industry stakeholders, and if you are a member, thanks so much for your support and participation. If you find this content valuable and for some odd reason you are not yet a member, consider joining NY-GEO at the appropriate membership level with details available at our website. The live recording from the NY-GEO 2023 conference will start in just a moment. Thanks so much for listening.
Great. Good morning, everyone. I appreciate you all stopping in for this exciting panel discussion. I'm not going to spend a lot of time up here. Really want to get into hearing from our experts here at the table. Just a list of our presenters. Today we'll be talking about surface water and wastewater heat exchange. With that, I'm going to hand over. You want to grab the mic there, Karl? Or actually, you're going to come up here. Hand over to Karl and Neubert to get started.
Good morning, everybody. I'm going to be talking about sewer heat exchange. Before I start, I'd like to thank NYSERDA and Donovan's team to reach out to us a couple of years ago and show an interest in our technology that would be beneficial in New York State's drive to decarbonize its housing stock and get out of fossil fuels. I'd also like to thank Matt and his efforts to put this panel together. And there were three gentlemen yesterday that already talked about, either directly or indirectly, about our technology. So it's a known commodity around here. And I'd like to thank all of you that I don't have to talk about how heat pumps work, because every other presentation that I give, I have to make sure that everybody knows what a heat pump is. But here it's not the case. We are a technology licensing firm. We do not manufacture any of the components ourselves. We've been in business since 2009. We were formed by a former engineering dean of a college, a concrete products manufacturer, geothermal engineer, and a mining executive. And I joined the team 3 years ago to promote this technology. So the technology has been around since 2009. But with the proliferation of natural gas as a clean energy source, we've had little chance to get a foothold in Canada. So here we are in New York to do this. The problem that we are looking at, and I'm going to add a few more here, are how can we decarbonize our housing stock? How to profitably cool and heat buildings using while meeting climate change targets? How do we pay for this new investment in infrastructure? And using sewer heat exchange for ground heat exchange with thermal district energy projects, replacing fossil fuels. Now, I'm going to add a few more problem points to this. Last week in Fort Lauderdale, you had major flooding as a result of extreme weather coming from climate change. 3 weeks ago, million people were out of power for 3 to 4 days up in Quebec. You've had the arrival of atmospheric rivers in Vancouver last year. I didn't know what an atmospheric river was until the area from Vancouver down to the US border was flooded. This time around, we already had 42 atmospheric rivers in California. And these events show us that our wastewater and stormwater infrastructure is not capable of dealing with these extreme events. What happened in Texas 2 years ago, what happened during Hurricane Sandy here in New York, are other effects of climate change, and we have a solution to deal with this. The value proposition is to provide energy savings while eliminating fossil fuels, integrating proven ground source heat pump technology with storm and wastewater energy recovery, reducing peak electricity demand in summer and winter, and providing stable pricing independent of carbon levies. As a bonus to this, we also provide a thermal storage capacity, i.e. a thermal cloud. You store the energy in the cloud, and then you can remove it the same way as you do in a computer. Our system has two components to it. One is below ground, and another one is above ground. The below ground component is powered by a heat pump. Heat is removed from a building and pushed into the heat exchanger, which is embedded in a sewage pipe. We took the slinky that is from a geothermal field and wound it around the core of the steel core of a sewage pipe and encased that slinky in concrete. And by connecting adjacent sewage pipes together, you form a thermal network, thermal energy network. So in summer, energy is moved into the pipe and the ground around the pipe. And in winter, we recuperate the energy from the pipe and the ground around it and move it back into the building. The hookups and so on, you're all experts at us, I don't have to explain this. The second part of our system is the integration of hybrid solar panels. As you all know, solar panels, when it gets very hot, lose their efficiency to produce electricity. By keeping solar panels at their optimum operating temperature, we're able to maintain maximum output on the panels while removing the heat from the panels for other uses. We can use the heat from the solar panels and push that heat into the sewage pipes and the ground around the sewage pipes. And I hear in New York State, you get snow once in a while in winter. We reverse the energy flow to the solar panels in winter and keep them snow and ice free. So by being able to keep the solar panels operational throughout the year and at a operating temperature that allows optimization, our system can generate on average 5% more electricity than an ordinary PV array that is just electric alone. The solar panels can be roof mounted, building integrated in our at-source energy wall, or ground mounted as you have it anywhere else. So we have installations in a campus setting in Sudbury, Ontario. This is at Cambrian College. You see the at-source energy wall on the side of the building, and buried below it is the pipe. On the right side, you see an installation at a subdivision, and I don't know if it's clear here, but you have the ends of the pipes that are being fused before they're being fused to form the district network. And currently, we're installing it at a seniors residence, also in the vicinity of Sudbury. Concordia University of Montreal is supplying us with two PhD students to study some of the aspects of this. So we're playing around with some of the fluids that are going through the loops. But we've been very happy with the performance of it. So as I said, it's an encased heat exchanger. We do not come into contact with sewage because the heat exchanger is embedded inside the wall of the pipe. The operating life of our pipe is a minimum of 50 years with no operating costs. So once the pipe is in the ground and fused and it's covered with backfill, it stays there until you have to dig it up again in 100 years or so. And it's the same installation as an ordinary sewage pipe. So if the only thing that installers have to do is fuse the HDPE pipes between the ends of the pipes. So that's the pipe. As I said, it can form the backbone of a fifth-generation energy system where the connected pipes throughout a community can be used to connect different buildings, and you have a load flattening of the system. We are qualified under the ANSI C448 standard. And as I mentioned earlier, we reduce peak electricity demand in summer and in wintertime. Summer, we replace air conditioners, and in the wintertime, we also replace the requirement to have supplemental heat like baseboard heaters because of the way we operate. This diagram was shown yesterday already by another presenter. It's available on our website. The energy panel is it's a hybrid panel that we attached a heat exchanger to it, and that heat exchanger operates as I mentioned earlier. In that example of that campus setting, at minus 30 degrees, the temperature behind the panel at that point was plus 20 Celsius, about 68 Fahrenheit. So throughout the year, the panels can provide ample thermal energy. This is the way the panels can function to provide warm water for a building. And the panels also can produce the energy that is required to run the heat pumps. So if you want to design a system with resilience built into it, the panels can provide the electricity. It can be stored in a power wall, or it can be stored in an electric vehicle. And if there's a power outage via a bidirectional charger, you plug in your EV and it runs your heat pump. So if there's an effect like Hurricane Sandy or whatever, you can still power your heat pump and provide heating and cooling. Our business model is we license manufacturer to produce the two components, the pipe and the hybrid panels locally, and we get a recognition for that. So we were written up in GEO connection. There was research done on us by one of the speakers that spoke yesterday. That's his master's thesis on our system. This slide is of interest. This came out of the European Union, and it says that just the waste heat that comes from data centers, wastewater facilities, and subways can cover 10% of Europe's thermal energy need. That's the equivalent of 6 billion barrels of oil a year. And the German government decided to phase out oil and gas heating. And this diagram looks a little bit familiar to the one that we've used, because I sent our diagram to the German government right after the invasion. And here you see the integration of the heat loop tying into the city sewer system and hybrid solar panels. So they just added a few more renewable resources to it to make it more appealable. It also ties in some other surface heat and boreholes. So this is our system, and I'd like to thank you for your attention, and anybody that's interested to find out more, talk to me or look it up on our website. Thank you.
Good morning. I'll try to keep pace here. My normal deck is very long because there's a lot of technology. So I'm Aaron Miller. I'm the Eastern Regional Manager for Sharc Energy. We're a Canadian company based just outside of Vancouver. I'm based in New York. I handle everything east of the Mississippi and up into Eastern Canada. I'll try to, like I said, try to keep this going. We pair beautifully with geothermal, so I'm really excited to be here. And I'll let you read these points, but really what we're looking to do with Geo is by using the sewer as an additional heat source, heat sink, we can shrink the size of a Geo field by up to 50% while still maintaining the same coverage. So we're reducing project costs massively, reducing the project footprint, and we are essentially turning the sewer into an urban Geo exchange field. And as they were talking about before, the investment tax credit available through the IRA, in addition to all the utility incentives, and here in New York, the Utility Thermal Energy Networks and Jobs Act is mandating the utilities get to work on pilot projects. So real quick about our tech, we have two product lines, the Piranha and the Sharc. The Piranha, essentially, you can think of it as a water-to-water heat pump but instead of using a condenser loop as your energy source, we're using wastewater. So for your typical multifamily residential building, we're intercepting the sanitary outflow, putting it into a wastewater holding tank, and using that as a thermal battery to pump the wastewater, solids and all, through the piranha, and extracting the energy out of it that way. We don't filter it, we don't chop it up. If it can flush down a toilet, it can go through our system, in and out, no big deal. The piranha does, though, and I've got a slide here in a little bit that shows it can pair up to a geofield to take some of that energy and push it back into a geofield. Let's say in a during a massive cold snap, we can use the piranha's wastewater hot water output to push energy back into a geofield to keep it in that optimal range. And the Sharc system is our larger system. It can be used for a standalone building, but really where its magic comes to bear is when you can tie it into a municipal sewer line, a lift station, wastewater treatment plant, because we're dealing with much larger flows. So, and one last point on this slide, you can see the throughput through all of these sectors is they make a lot of wastewater and they need a lot of hot water. So hospitality, hotels, hospitals, commercial laundries are a no-brainer for us. So anywhere you need a lot of hot water and you make a lot of waste, we're a good fit for you. Here's the piranha real quick. It's a specialized evaporator tank. Basically, like I said, all the solids, all the wastewater goes in. Heavies sink to the bottom, get flushed out multiple times a day. Anything that floats goes right over the top, out, back down to the wastewater holding tank. And then we just extract the energy using a refrigerant sheath that's around the tank to then push it through a typical refrigerant compressor loop to get more heat, and we can push up to 140-degree potable hot water out of this box. And this is what a typical above-grade piranha looks like. There's your wastewater holding tank. It doesn't have to be below ground. We just like to have the piranha above the tank. Therefore, we can use gravity to flow back out because we're trying to maintain the building's gravity-fed outflow. We do not want to get in the way of the actual sanitary flow from the building. And I've got a little example from Lake Louise. It's a hotel in the Canadian Rockies. We're supporting 4 commercial laundries, and basically we've cut their energy costs by 60% just by using the hot water coming out of the laundry machine, running it back through our system to then make hot water for the washing machines. So now the boilers only cycle like every 45 minutes as opposed to every 5 minutes. So massive savings, and they love us up there. And this is a net zero building in Boulder, Colorado, where they're using our piranha to supply domestic hot water for 37 residential units. And here's that slide I was telling you about before, how we can use the piranha's secondary connection to pump hot water back into a geofield. This is it's an extended use of the piranha. It's really designed more for the standalone building. So it's cool for geo, but not really the game changer. The Sharc system is where things happen. Real quick, everything you see on the screen comes from our factory. Does this thing have a? Oh, it does. Nice. Wastewater gets pumped through into a macerator pump that's behind this control panel, gets chopped up to about 3/4 of an inch, pushed into the Sharc, which is this box here. It's a very specialized filter. There's a small motor that turns an auger and a brush that basically forces all the large solids down and out to city sewer, and then anything that gets pushed through this basket filter is now no larger than 3 millimeters in size. It goes through a piping and valving section and into a wide gap heat exchanger with plates are 8 millimeters apart from each other. So by keeping the scrubbing velocity up, we're able to keep any suspended solids in that warm sludge in suspension, so then it can just pass through the heat exchanger, and then we can just basically cycle it back out to city sewer. And because the Sharc can operate in both directions, we can do heating and cooling just by reversing the flow. So in this diagram, you see that we're taking energy from the sewer and pushing it through the Sharc and into the building, taking the cold, the return through the Sharc and down out to city sewer. And then by reversing the flow, we're now able to take rejected heat from the building and now dump it into city sewer. And now when things are really happening with Sharc is when we use the city sewer to create an ambient loop. This is an example, National Western Center in Denver. There's a massive, municipal sewer line running past this old rodeo yard. We intercept that, run it into 2 Sharc 880s, and that is now creating roughly 3.8 megawatts of energy transfer that's supporting a mixed-use commercial campus that's growing, and they're planning to expand it to 10 megawatts in the future. And we're doing this outside of Vancouver. A large piece of land was given back to one of the native nations, and they're creating a large mixed-use campus that's going to be completely heated and cooled and domestic hot water production only using the city sewer. So it's really exciting. And this is the slide that I wanted to get to as quickly as possible, because this, to me, is the future of decarbonization at scale. This is what the Utility Thermal Energy Networks and Jobs Act is about. This is it right here. This is what we're looking at in a village in Westchester County. I don't want to say the name just because I don't want to jinx it, but they were old sewer line. They're going to be replacing the sewer, and in addition, they're going to be digging a geofield. And the developer has plans to put an ambient loop under a large portion of the city. And what they're in the process now of validating our study, which showed that by putting a Sharc in between that sewer line and the geofield, we can cover the same amount of square footage in the city, but with half as many boreholes. I think it's technically 47% less boreholes. So the developer loves us because we're cutting the upfront costs of this project drastically before we even start the project, which is great. And we're in conversation, not just in New York, but across the country, with ESCOs that are looking to do these types of projects. They're expensive, and their costs, their time, they eat up a lot of time, a lot of effort. So a lot of towns are looking at this and saying, how can we do this? Because 35% of New York State is going to be labeled as a disadvantaged community in the next budget go-around. Not sure if anyone knows that. Need to wrap it up. So the ESCOs are coming in. They want to buy up these projects, full stop, from development, deployment to O&M, and basically sell back the service to the township or to the campus, what have you, as a utility, for the next 25 years. So this, to me, is really exciting. This is what I'm chasing down in New York. I would love to talk to anybody who wants to see how we can incorporate wastewater energy transfer into GEO exchange projects. And so thank you for your time, and I'm really excited to be here. This is great. It's quite all right. We're here. Let's keep moving down.
All right. How are you you want to key this up as right? Yep. Presentation. Okay. All right. They got it fixed for me. Thank you. My name is Cary Smith, and thank you for being here. I'm with the GreyEdge group, which is kind of a international think tank, I guess is a good way to describe us. We solve problems, and what I'm doing is Aaron and Karl have given you some background, and what I'm planning to do is really kind of show you, and I want to stimulate your thought pattern and see what we do, okay, and why we do it and stuff. And we're going to talk about the ponds that are going on here in New York, which we're looking at district systems and how we can apply this. Each of these systems you've seen so far are considered to be plug-and-play components to our central loop or to our one-pipe ambient temperature loop. We call it the thermal highway. So anyway, I want to give you an idea why. Well, we can turn around and, we can take this loop and we can add and remove energy from buildings. We can add and remove energy from ground loops. Ground loops, interestingly enough, change from being sink and source, to storage. Consequently, we need less ground loops if we do this incrementally, and we look at it, and there's a reason for that. But we're also going to concentrate on wastewater today, and some of the solar photovoltaics, whatever we're going to have solar thermal to do this. But all these components here are units that go in energy sources in and out, and they don't need to be full size. They need to be incremental size to look at it. And we want to look at part load, because part load is what happens about 85% of the time to 90% of the time. In other words, we're showing you a curve. We call it the 50-90 rule. And it's basically the European model or the U.S. model and the European model that we have. The graph is on the curve, is a U.S. model, but basically it says that 50% of the load will handle us 90% of the year. And if we look at part loading on these systems and what we can do, incremental assets become extremely important and stuff. We can take a 100-ton incremental asset, like 100-ton from Karl's sewer system. If we trickle charge it into the main loop for 24 hours a day, we have 2,400 tons of per ton hours that we have put back in that system. And we can use water, we can use wastewater, we can use small amounts and turn around and actually make a use out of them because we do take them for 24 hours. And this is basically a bin graph. It's New York LaGuardia. We can see that 6,960 hours, we're in part load, less than 50%. And we take advantage of that and stuff and using wastewater. So every asset you look at, the Hudson River, those ponds, the sewer ponds, the waste ponds, everything that are sewer, all these are additive to this, and we can start to look and reduce the amount of energy we need by using these incremental assets. And incremental assets using what we call the least energy path. So that's what we're trying to talk about. As you look at that, you can start to see what the impact of this is. That things get smaller, things get less complicated. We have systems that run on two factors, flow and temperature. That's it. We can monitor it. And a 2 degree, 3 degree split around a system like this is a big deal. It takes very little energy. Most of the time at Colorado Mesa University, one of our flagship programs, we have a 4,000 ton system, 18-inch pipeline. I have a 50 horsepower pump running at 20 hertz, about 9 horsepower. Most of the time, I'm driving this system because of the low friction losses. Anyway, some see a pond. We see emissions free. I want to thank AWUB Supply, by the way, for these slides and stuff. This is another heat exchanger, and we're going to talk about surface water first. Well, how can we install it? It's just to show you some ideas that we have. Here we have it up north. It might work. Got a hole in the ice and go drop some loops in. Or as we turn around, we talk about looking. Drop some plates in, whichever way we go. So its use of the surface water, can we use it in one environment? Almost every environment in the temperate zone, without question, that these increments can be additive to us. Not only do we have the heat generated in the water, but we have the latent heat as it turns to ice. So, example, Olympic Center in China. The heat exchange is all done under the dock. They're place hanging for the entire building that you look under, 600 tons, as we sit through that. How about the Nashville airport? 3,000 tons that we've done in an old, we've gone about, I think he's several miles, 2 miles away. And stuff, we have a pit, it's an old quarry, and they drop the plates in the quarry and stuff, and then feed the airport. It's this wastewater and creative thinking about how you turn around and handle these assets that really makes a difference. Okay, largest loop system in Australia. That's a recognizable building. We've seen that before, Sydney and stuff, and we talk about doing this. There are applications for this in the inner city and some stream. Okay, so wastewater is a source thing. I'm going to talk about Sharc a little bit. I'm going to talk about some of the different ways. There's tube and shell. Karl's got a wastewater heat exchanger that he's looking at. Each one of these products could be used in tandem and sized to make sense when you go that, because we're not going to use it all the time, or we use it all the time, but we're not going to use it to solve all of the load problem. So 24 gallons of hot water a day for every individual average person. That's a hell of a lot of water if you think about everything we do that's going through those pipes. And 40% of the load is not unusual for us to look at downtown Manhattan in a high-rise building. The water and wastewater could provide up to 40% of the ultimate loading, as long as I have thermal storage to take advantage of the flow times. And that's the key portion. These products alone don't work as well because there are times we can't use them. However, if we make it smaller, we trickle charge, we look at what happens with the whole loop system, it's additive. And if I have a thermal storage, i.e. borehole system, to do that and hold it and stuff, I can use it all day long. So this is a Sharc. We've already talked about it, all these good things. It can be used as a cooling tower, a boiler. It goes both ways. So can the sewer exchange we talked about. And what I liked about it was this picture, because this is the idea about how sustainable it is. This is a picture of the bin that is inside the Sharc after about almost 6 months of operation. That's how clean it is. That is just open up, and that's a picture of what we saw. So, you know, it's really processing the water. It doesn't matter. It doesn't mind the sludge and all the other goodies that go with it. And then we have the Latte Tower in Seoul, Korea, one of our projects, 123 stories. It's about 10,000 tons. A third of it is from potable water, a third of it is from geothermal, and a third of it is from wastewater. These are using assets we have adequately to turn around and manage our problem and manage the whole. So, and that's the picture of the, you thought I'd like to see the foundation for that Latte Tower. That's taken from the hotel above it. Those little things out there are huge earth movers. So about a half a mile long. Okay, you know, we have a full building in Washington, D.C. that runs under the Sharc system. Okay, the wastewater building is their job. Anyway, and then, for example, we're looking at sewer heat recovery and stuff in Seattle, and this is a map of the sewer system and the way we would be able to distribute the energy through the system. So, pretty much, that's what it was. I want to give you some ideas. I want you to think. I want you to look at your stuff and say, what can I use that for? How can it be used? And don't ignore it and turn your nose up at it if it's a small source, because it can be very valuable. Thank you.
All right, it works. All right, so the Karl and Aaron and Cary, you know, there's a lot of opportunities with these systems. So I guess I wanted to try to give you a little bit perspective of what our experiences have been in trying to integrate some of these things. And it's not being discouraging. It's a little bit of like, hey, this is what you need to know to kind of go into this like eyes wide open of like how the roadblocks and some of the challenges that you can get into with looking at these types of systems. Said kind of, you know, that's the question. Is the juice worth the squeeze? Is the amount of heat that you can get from these type of things? We'll get into some of the details. The short answer is yes, but. So we're going to talk about the but a little bit. So yeah, it's like, why are we bothering to do this? Obviously, you know, Cary showed some of the advantages of like tying these things in the ambient loops, and there's a lot that you can do with it. And a lot of it is, once the infrastructure is there, it's basically free heat. I mean, you're talking about a little bit of pumping energy, but in comparison to kind of traditional heating sources, there's just a tremendous amount of heat that are in these flows. You know, for example, you know, we look at like a medium to smallish wastewater treatment plant, like a 40 MGD wastewater treatment plant. Even if you say, all right, we're only going to touch like half of the flow going out of that wastewater treatment plant, you can do almost 100,000 MBH of heating of that. Like, these are not small amounts of heat that are available. And so that's why, you know, it is worth kind of going to some of these great lengths to look at these sources, just because the opportunity is so substantial there. There's a kind of gradient of different wastewater streams. You know, you have everything from, so on one end of the spectrum, you have kind of black water. So that's the sewer as it's out in the system. It has everything that you expect that's into it, and that's where you get into systems like the Sharc that are kind of able to handle everything that kind of comes with those flows. The other end of the spectrum, you have basically wastewater treatment outfalls, which is after all the water treatment has happened, and then basically all you're doing at that point is just dumping it into a body of water, whether that be a lake or a river. It's treated water at that point. If we can touch that water, it's
it's at a very reasonable temperature. So this is actual daily temperature data from a project that we're looking at, where, dead of winter, polar vortex 2014, that water going out of wastewater treatment plants, it's still like 48 degrees. So it's very, there's some seasonal variation, but it's very, the swings are very muted in comparison to what the ambient air is doing. So, but these things aren't exactly always where you need them to be, and so that's one of the challenges. One of the other things is, how do you actually access these flows? Because to put something through a heat exchanger, it needs to be a pressurized flow. So how do I take my sewer flow, which is generally by gravity? If you can grab a force main or something that's pressurized already, you're golden. But most times you're going to be looking at a gravity flow, and I need to turn it into a pressurized flow, which means I need something that's going to interface those two things together. In most cases, it's going to be some sort of wet well. My wastewater guys love me because I ask them these crazy things of like, hey, what if we did this and this? And they kind of look at me like, wait, you want to do what? And then you kind of explain what the why is, and they, they're coming along now with it. But there's a lot of infrastructure that goes into this. These are generally large concrete structures that you can't just put everywhere. So there's a lot of challenges with trying to find the right flow in the right spot with the siting and where you can use the flow and it's available. There's guidelines from the Hydraulic Institute that are very good, and they're very prescriptive of like, given this flow, given this style, here's what your wet well would look like, and that helps understand a little bit of like how to, like what size structure you're looking at for whatever size flows that you need for your project. Especially, we're in the Northeast, so a lot of our systems are old combined sewer overflow systems. A lot of them are fairly deep, especially in the urban areas and where a lot of the large loads are that we're trying to serve. The sewers do tend to be fairly deep, and accessing those can be a challenge, especially in dense urban areas and where you have streets. Trying to understand where there might be existing work going on is really valuable, because if you can combine in on something else like a sewer main replacement, like that is invaluable to kind of just be able to piggyback on that. Because if you're the only reason that you're going in there, it's a very expensive proposition. And not to say that it's not possible, but like there's a lot of dollars involved. And so in trying to sell that to the municipality and trying to make the financials of your system work, it's another thing you have to consider. And then what exactly is going to go above ground? Who owns the land where you need it to go? What's the zoning in that area? All these things they have to kind of take into consideration, because you can't just plop these things down anywhere. And that's one of the biggest challenges in trying to do the feasibility of a lot of these larger systems that we're trying to work through. Rivers and surface water. So there's kind of two major styles. Obviously, there's the plate and frames and like the slinky type systems that Cary was mentioning. So obviously, if you have any moving water, that's going to be an advantage over still water, because it's just a different heat transfer mechanism, and so it's going to be a lot more effective. But if we're talking about doing heating in the wintertime, your approach temperatures are going to be pretty low. So you're going to need a lot of surface area to do really much of any heating out of that. So that's just another design criteria you have to work around, just knowing that like you're going to need a lot of surface area, meaning you're going to need a lot of that, whether it's a plate and frame or slinky, you need something that's going to provide that surface area. Because if I have a river and it's only 34 degrees in the wintertime, it might not freeze over, so like you have that working for you, but it's a pretty small delta T. So we can pull heat out of it. It just takes a little bit of work to do it. Obviously, if you can do direct heat exchange, if you have a mechanism from doing that, you can do a lot more with that. But now you're in a completely different permitting regime that is not impossible, but there are a lot more roadblocks to it, and you're going to have to really prove your case. The regulations are a lot more strict than some of the systems that kind of exist already, as far as intake structures and like what you're allowed, the velocity you're allowed to suck the water in at, for good reasons. And then also you need to kind of show that the thermal impact that you're going to have in whatever body of water that you're in is going to be acceptable. A lot of the conversations we've had with permitting authorities, they're more focused on adding heat in the summertime, because they see that as a much more detrimental. effect. The taking the heat out in the wintertime, there's been a less of a concern about, so most everyone is going to focus on the summertime impact of it. The other thing was one thing that someone brought up yesterday, especially with the plate and frame heat exchangers. You want it to be one of many heat sources you have, because just like a air source heat pump, if you run it real hard in the wintertime, it can ice over. So what happens when it ices over? You have to have a means of defrosting it. So it's just one of the things you have to kind of make sure that you have a variety of sources so that you can basically give it a rest. The other thing is, with these larger systems, we're becoming a utility. So one thing that existing utilities is expected of them is that they're available all the time, they're resilient, they can provide the service that you're promising all the time. So if you have something that's intermittent, whether it's the river heat exchange and you need to be able to kind of like turn it off to let it defrost, or a sewer flow that might not be consistent, you need to plan for that inevitability that some of these other sources might be available, but you need to still provide heating to your customers, or else you're not going to have customers for very long. So there's a lot of, in the planning process, making sure that you have a plan for backup, have a plan for if your power goes out, have a plan for basically dispatchable heat, so you can make sure that you are providing heat. Heat is a life safety thing. So you need to be able to provide it to your customers all the time. So it's things that you have to consider when, especially these larger systems, and we're talking about becoming utilities, that we really need to think through. So we will now open up for questions. I'll give it back to you.
Fantastic. So we want to now open to the audience for questions. There's already a hand all the way in the back of the room, Matt. Hurry.
Run it.
Everybody's eager to ask questions, so we want to make sure.
Good morning. Elizabeth McCorvey, Executive Director, Family Resource Center, Peekskill. We're 50 minutes away from New York City, and I've been doing this work for 22 years. Our not-for-profit has 24 low-income units and scattered sites, and I wanted to know, we were interested in another 36,000 square foot building that's owned by our local billionaire, Louis Lanza, in Peekskill, New York. It has a problem with the basement flooding, so can you tell me if the water could be eligible somehow to be wastewater to pump it up? Because our Italian electrician for over 20 years told us the building's is worthless because of the flooding in the basement.
The answer is yes.
Yes.
We have a building in Salt Lake City just like that, and we take the water and we dug a sump in the basement. We started pumping out, using it for heat exchange, direct exchange through. Well, at that point we didn't have to use the heat exchanger. It was clean enough, and it was not potable drinking water, and we got about a third of the energy that we needed for the building.
Who else has questions? While you're back there, then next up here.
Mitch is driving this. So raise your hand for Mitch.
Hey, so Sam Gerber with CDM Smith. I understand that it's hugely application dependent, but as a general ratio, what do you see between the ratio of BTUs that you can recover from one of these systems to the heating load of the building? Like 10%, 20%?
Not quite sure I'm following your question. I know
So-
that I can say with confidence that it's all application dependent. We can pick up the entire thermal load of a building, of a campus, of a town, if you have, as Cary said, it's about flow and temp. If I've got flow rates and the temp in that water, it's amazing. And we're literally using kW of electricity to essentially transfer megawatts of heat thermal transfer. So it's an exponential COP, really, if you get down to it.
Okay, but all that sewer water is not coming strictly from the building that you're heating and cooling, correct? You would have to pull that sewer water from somewhere else as well?
I'm sorry to say it again, but it depends.
Okay.
Like, so if you have an apartment building, let's say with 500 to 700 units, a big building, there's a lot of flow in there. If you got space for a tank to capture the peak flows, you can pick up the entire thermal load of that building. We never want to be the only game in town. We always want to have redundancy, backup, top off and start off. But yes, if we can tap into the sewer, and this is we're how do I put this lightly? We're trying to get discussions with the DEP of New York City to let us tap into the sewer line like they let us do in DC, Toronto, Denver, Seattle. That's going to be the kicker. So yes, when we can tap into a force main or a municipal sewer line or a wastewater treatment plant, you can. It's limitless. Actually, it's amazing how many equivalent KW are being flushed down the toilet every day.
Interesting. Thank you.
So we have one up here. We'll start with Anthony. Still good? Hold on. One moment. We'll wait for the mic.
Hey, so my question is based on, I did a project that I developed on Zero Place, which I'm not going to get into details because of the presentation later on. And in the initial space, I was looking at this waste energy stuff, and I could not make the mathematics work. I mean, I have a good background in physics, and I had all these crazy ideas of how I wanted to make these storage sewage tanks and develop ideas that you now have on shelf. But the numbers didn't work. In the end, it was much cheaper and simpler to go with straight bore fields. And because we're in a cooling dominated climate, it was actually ended up getting my domestic hot water for free. So
Contact me and we'll set up a video call with our technical team and we'll answer those questions.
Another backup question is, what happened when you freeze the sewer? Obviously, you can't do that.
We don't freeze it. We don't. We set there's a low limit level, so you don't push out, and it's regionally dependent. The authority having jurisdiction is the one who tells us how low we can go. But generally speaking, we try to no lower than the 43 degrees outflow. And again, even with, we've proven it out in DC that people were afraid, we're afraid you're going to be, making the sewer too cold to affect our. We're really, even though we're grabbing so much energy, we're really a drop in the bucket as far as like the amount of flow that goes by a day. So you'd be hard pressed to freeze a sewer. I mean, I'm more concerned actually of dropping the temperature out of an individual building because I don't need a popsicle basically clogging up the sanitary outflow. So, but that's why it's all fully automated. We set low limits at like 43 degrees basically.
And it doesn't affect the digestion that they need for the digesters or the treatment plants?
No, and for us, and again, I'm sorry if I'm dominating, we deal with the influent, not the effluent. So we want to deal with the untreated wastewater because we don't want those biologicals, those dead bugs essentially. They turn into jellyfish and they'll clog up a heat exchanger right quick. So we're trying to deal with just the raw, unfiltered sewage, bricks and all.
Okay.
Hi, I'm Kim Frachek, the director of Sane Energy Project. Oh, sorry. I'm sorry.
In general, your problem is not freezing the sewer, it's overheating the sewer. That kills the bugs. The cold just puts them to sleep.
Good point. Thank you.
Okay, thanks. Director of Sane Energy Project, we fight gas pipelines in New York State, and we're being very successful here. I have a question for Aaron. I was really excited to hear that you're trying to get in to talk to New York City DEP. So we should talk. Use us activists to get in because people in our team that are fighting pipelines in New York City work at the DEP, and so let's make it happen.
Yes, please.
Okay,
yes,
awesome.
Please, yeah.
They're 2 rows behind, Matt.
Oh, also one more question.
Sure.
ESCOs, are they have a historically predatory sort of vibe when they are in business. Would you be more interested in working with municipalities as opposed to ESCOs?
Well, I always joke that we're a Canadian company, so we have to be nice by law.
Okay.
So I want to work with everybody. Anybody who wants to get stuff done.
I got you.
We're
Okay,
literally
cool.
trying to stuff 40 years of progress into a 5-year window. Yeah. Thank you, President Reagan. So, yeah, I mean, it's funny you mentioned that because I was actually hesitant to use the word ESCO because it's almost like a bad word, but it's an energy services company. It's people with, there's billions of dollars of green money, literally, that want to come into the market. It's just a question of setting those, those market signals, if you will, to get things going. But like I said, 35% of New York State is going to be a disadvantaged community. There isn't time or really money to get this done on a municipal level or passing the hat around. We need these big moneyed interests to come in and do it. So, oh please, thank you.
We're very fierce too.
And I'm too nice. So,
given a couple assumptions like that were offset as natural gas at a normal pricing, what's an ROI that's expected for a community in general? I mean, I know there's a million variables, but when you throw a $5 million project in a project, what's our ROI typically?
You decide on the ROI because you're going to be charging an energy levy for the users of the system. So you can decide the amount of money that you need to make.
My question was, given a particular installation, we're offsetting a cost of energy, natural gas in my case. And that takes so many years to offset that added capital to reclaim the energy. That's a simple reality. And forget about subsidies and all that other stuff. That's part of a formula, I understand it. But when we get up in the morning as an engineer, we say cost in, investment, return. That's my question.
Well, a typical system that we have is about 6 years. For a natural gas pipeline to be dug, laid in my area where I'm in Northern Ontario, it's 40 years. That's the so there's your comparison. But the owner of the infrastructure sets the selling price of the energy to the user. So that you can give it away for free, but you can simulate it with the gas prices. So it's.
Yeah, I was just going to add to that. I mean, like that's a little bit of why the utility thermal model is so attractive right now, because in a lot of cases, you're taking things at scale that are very specialized pieces of equipment, trying to do them at large scales that you wouldn't be able to do at like a single building level. Give everyone access to sources they might not have, but doing it in a way where a utility can take a longer view of like a payback, but they can pass that along to a customer, make them easier for each customer to attach on and make their ROI a little bit more digestible from like a commercial perspective.
This is Xiaobing Liu from Oak Ridge National Lab. Very interesting panel discussion. I just want to give comments. For this wastewater, it's not necessarily has to be just the sewer water. Some the reclaimed water can also be utilized. Denver Museum of Science, they use this reclaimed water for their heat pump system. It works since the 2012. It works fine. And another thing is the abundant mine water is also another resource. Can think about use this similar technology. DOE just announced a $500 million demonstration project for using this mine water as a source, to either provide heating, cooling, or other way. So maybe this is another thing. If you have that resource, you can think about that.
The problem with mines is they're usually not in populated areas. So they're and we do have mines in Sudbury. Sudbury is the largest nickel producer in the world. So but we don't there's water in there. So we should be looking at that. But we won't get any money from the US DOE to do that in Canada because we're still subsidizing fossil fuels. So for us, it's going to be a downhill battle to get this water out. But it's a very good point.
And I think that falls in the category too. There's believe the phrase is everything, everywhere, all the time is what the sources that we're looking for here. So it's basically everything is on the table, including these applications.
I have a question about the chemical analysis of the water as a wastewater you are using for the Sharc tank. So based on the pH or chemical analysis is not affecting the life of the device, or it can be modified for all type of water, like the mine water that he mentioned?
The short answer is yes. There are. It's a stainless steel. So long as we have an intake form, and one of the things we ask is like, tell us about your water. If it's just typical sewer water, no big deal. But if we're working with an industrial plant, I'm looking at a car manufacturing and paint plant, and they use some really nasty stuff. So we're having to be smart with where in their waste stream we're capturing that waste stream, the wastewater, because in certain parts of the process, there's like some corrosive material that does not do well with stainless steel and the rubber gaskets. So for the most part, any water is good water, but there are some elements, like I said, either the effluent of if you have biologicals can be a problem, or again, certain caustic chemicals. But for the most part, you can't scare us.
Okay, thank you.
We're generally dealing with the nastiest water imaginable.
Sarah? Sorry, her hand first.
This is a totally non-technical question. It's listening to this conversation, which is all new to me. I'm Sarah Collada with Siemens Smart Infrastructure, so I'm one of those ESCOs, the kind that develops clean energy projects, very comprehensive, large scale. And it sounds to me like this is a thermal microgrid. The world now kind of uses the term microgrid, understands electricity can be sourced, stored, and used in a variety of ways with a lot of controls. And this is it's new to me. I think it would probably be new to quite a few of my colleagues, including my engineering colleagues, but it's so valuable. And I'm wondering if you're starting to use that term, thermal microgrid, to help communicate, to help build some awareness and literacy about this way of thinking, because it's such a different way of thinking.
I think we call it the thermal highway. And yes, we do. The purpose is that we can take all of these assets and use them at the right place at the right time and come up with a total solution instead of a partial solution. One point I'd like to make is we could look at geothermal at installation. If we were to go 50% of the load, we will decarbonize over 50%. So your first shot at this is the big bang. And you can use all of these technologies together to use a little bit here, a little bit there, and make it. And again, I say that as long as you've got thermal storage with this, some sort of boreholes or tank or whatever have you, you can swing it to handle the whole year. And the problem with any of our technologies, the sun only shines half the day. The sewer only peaks 3 times or 4 times a day. So we can use these assets all the time and stuff and basically trickle charge our systems. And that's really the solution to this. It's a little bit here, a little bit there, and stuff, and putting them together, always using the least energy path, the lowest pump power, the lowest amount of friction you can put in the system. Make the affinity laws work for you. And that's my non-technical answer.
The official technical name for this network is a 5th generation thermal energy network. So you can Google that, and then you get those diagrams and reference sites around the world where we have it.
But it's a great point, and I agree that, like, you saw my eyes roll up when I tried to say utility, Thermal Energy Networks and Jobs Act on all these acronyms. So yes, there is definitely a marketing component to it, just to kind of simplify it, because like I told you when I first started, like, my normal slide deck is really long because it's very technical and people start falling asleep. So the easier we can make this for people to wrap their brains around, yeah, I totally agree with you. So any help you can provide in that direction. We're all energy nerds, and it's very easy for us to just kind of ramble on about delta T's and approach temperatures.
We've been dealing with a large municipality in New York State for the last 2.5 years to see if we can put a demonstrator in. And we're very close to announce it. I can't announce it right now, but we're in the final stages of that. So it's coming. But what all of you can do is talk to the elected officials to provide incentives for municipalities to install this hardware right now. Every time any government gives a subsidy to a municipality to install wastewater infrastructure, they should have a provision in there that this wastewater infrastructure has to have the capability to tie into one of these networks. Problem solved. Everybody will have to do that. Otherwise, they wouldn't get any funding for those for that. So if all of you contact your elected officials, be it municipal, state, or federal, and say, please add this to your funding bill for this year, or for your for your funding bills for other years, it will happen faster because people will be forced to install that infrastructure. You don't have to use it right away, but whenever somebody is ready within that municipality after it's been installed, hookup is simple. It's as simple as hooking up a gas furnace.
Okay, last formal question for the record.
Hi, I'm a consulting engineer, do energy projects. I didn't hear you guys talk about the useful temperature that comes out of each of your systems, and if you could talk to that, right? So if I'm going to capture the waste heat, is it 60-degree waste heat? Is it 90-degree, 150-degree? So for each one of your options, could you mention that?
Yeah, looks like, so the typical wastewater out of a multifamily residential building is roughly 70 degrees Fahrenheit. Pretty much, doesn't matter what part of the country in or what time of year. Municipal sewers are a little bit more variation depending on region and time of day, as you were saying before. But Washington, D.C., for instance, I know we've got really good data, and it stays within pretty much a 10 or 15 degree window the entire year, anywhere from 45 to 55 degrees. Even on like major snow melt day, you'll see a quick spike in flow and drop in temp, but not out of that useful range. And then on like a late summer rain, when all that energy gets washed off of buildings and into the sewer, you'll see a spike in the temperature. But for the most part, you're staying there. And our system can output up to 140 degrees on the Piranha. The Sharc, it's a heat exchanger. So we can make neutral water, and then it's just the heat pumps you connect to it that will then make the hot water. So for instance, in Vancouver, at the False Creek, we're using specialized heat pumps in series to make 180-degree hot water that we're now feeding a massive loop of downtown Vancouver with. So, the Sharc, it's really depending on your heat pumps. The Piranha, we can set point up to 140 or down to 90 or 100 if you just want to do preheat.
I just thought I'd make this easy. We don't use any antifreeze in the systems, so they're running at about 50 to 95. And that's the ambient delivery temperature. Those loops can take any temperature these gentlemen can output, and they can generally take any temperature we can give them. So it doesn't matter on stuff. We can even use high temperature focused solar thermal and trickle charge that into the system. So what happens is the bigger it gets, the more versatile it gets in general.
And for us, the majority of the source of heat that we put into the system comes from what? Oh, wrap it up. Okay. Cary answered the question already.
Oh, now I feel bad. Thank you, everybody. I appreciate it. Thank you, panelists. Please give them another round of applause.
That was going to be my answer anyway.
Exactly.